Hi, I'm Carrie. I'm a grad student at Johns Hopkins. This work has been done in collaboration with Rachel and under the wonderful mentorship of Elena, Martin, and Jason. So I'm happy to be third in this group. So you have already heard about the simulation. You already know there's a bar. You already know that resonances are moving in time because we have things that are changing their pattern speed in time. The work that I did throughout these 4 weeks was really just exploring resonance-induced radial changes in the simulation. So, as previously mentioned, this simulation has a bar and a spiral. And if you have a bar and or a spiral, you will be having radial changes in your galaxy, based purely on the fact that bars and spirals move angular momentum around. So stars are going to have to move to, deal with that. There's also the fact that you have a potential that's changing in time. These kinds of secular changes are gradual. They're not, sudden jumps in a radial location, but it's sort of a slow procession of pericenters or apocenters, et cetera. What I actually wanted to focus on for this talk is resonance-induced radial changes. These are more localized in time. So you have a star that's kind of hanging out in its current orbit. Something happens, it interacts with the resonance, and it changes its radius kind of suddenly, so over a shorter period of time. There's this classical picture of this called radial migration that was first discussed in Selwood and Binney, 2002. It was actually taught to me by the wonderful Kate Daniel, who I thought would be here in person, but it seems she's here in spirit. But if you have questions, you can also ask her about that. So in this picture, it's, in my mind, a little bit idealized where you have a spiral and you have a star that's on a nearly circular orbit. It's getting trapped in the co-rotation resonance and eventually getting booted to a new radius, different from its birth radius. However, in a galaxy, you have multiple different resonances. As you saw in the nodes, there are a lot of different resonances you can interact with. You have resonances from the bar, you have resonances from the spiral, you have, the famous inner and outer Lindblad resonances, the famous co-rotation resonance, but you also have, funkier things. You have 3 to n resonances. You have really a bunch of different ways to have a resonant interaction that's not going to just be this really nice, beautiful picture of star near co-rotation gets moved by spiral arms in a horseshoe orbit. So I wanted to look at these funky guys. And you might ask, do we have any actual observational evidence for this? The answer is yes. So even in the first paper, the Selwood and Binney paper, they use it as a way to try to explain stars near the solar neighborhood that seem to have been born at different radii. So if you assume that we have a beautiful, nice, smooth metallicity gradient in the galaxy, radial evolution would sort of mess that up. So if you have stars that have resonance-induced radial changes, they're going to be moving to radii far from where they started, and that's going to be messing up your beautiful, smooth gradient. So what we're looking at are simulations, again, already discussed by Rachel and Binod. And simulations give us a chance to actually follow a particle for billions of years, which we don't get to do in the Milky Way. We get to see them for our lifetimes. That's it, not even close to their lifetimes. Simulations also give us a chance to get a handle on statistics. Specifically Jason's simulation, because there are millions of particles, we can actually see stuff in a population sense. And it's closer to what we would see in the Milky Way. We're getting closer to being able to make actual things that we can relate to the Milky Way. So, as I mentioned, if you have bars and or spirals, you are going to have things move. So this is just a nice plot of 15,000 stars that I selected in our galaxy and the distribution of their pericenters and apocenters at 1 gigayear and at 4 gigayear. So throughout this talk, I'm going to refer to 1 gigayear as my air quotes start time for the simulation. This is after the bar is formed. I care only about the secular evolution from the bar and the arms. So it doesn't really matter to me that there's stuff before then. So we're looking only after these structures have formed. So if you look in red, you have the 1 gigayear distribution. And then if you look in blue, you have the 4 gigayear distribution. They're not the same. You've had radial changes. You've had radial changes due to just this sort of gradual, what I'll call bulk change from the fact that you have these structures, but you also have some of the resonance-induced changes, which are going to be smaller in number, but still present. You will see that you're sort of, on average, moving in, but you also have this longer tail, which is interesting. So the goals for this project were to try to get at how do the radial, how does cellular evolution change the distribution of stars in a galaxy over time? This is the observationally based question here. Me, an observer, what am I going to be seeing? What can we predict from this? How can we, get at estimates of how many stars move from where to where, why? What are the statistics here? What are particles having, stars. What stars are having resonant interactions and where? And which resonances are causing these interactions? So to try to get at this, I select disk stars and annuli. So I just chop up the disk from 0 to 8 kpc. The disk does go all the way out to 30 kpc, but bite-sized pieces here, we're starting 0 to 8. It's also where the bulk of the structure is. So I take half kpc annuli, 1,000 stars in each annuli, and then I follow their pericenters and apocenters over time. This is my air quotes, poor man's orbit, because I'm not freezing the potential, which is computationally expensive. I'm not computing the actual full orbit. I'm also not actually calculating the frequencies, but this gives me a handle on the frequencies in a way that's, pretty easy to do. So then I fit a plot of the pericenters versus time and the apocenters versus time with a line. A line is not going to be the best fit here, but the line will tell me, how are these things changing in time? Is it gradual? Is it fast? What's the steepness of this slope? And then I take some threshold. I take this threshold to try to get rid of that bulk movement, the slow, kind of small movement, the shallow slope. And I want to look at stuff that's moving a lot. So I take some threshold, cut out, hopefully, the bulk of those gradually moving stars. And then I fit a sigmoid curve. So why a sigmoid? So I think that a sigmoid is a good idea here because it kind of captures the movement that I think we're looking for. So we're looking for things that are just kind of hanging out. They have their apocenters or pericenters at a certain distance. They kind of bump around there for a while. They have a resonant interaction. Pretty quickly in time, they change to a new pericenter, apocenter, and then they just kind of bump around there for a while. Of course, this doesn't capture the whole family of things that we expect to see. This is also really rudimentary. There's better ways to do it, which I'm going to talk about more later. But this was a good, first jab. What can we actually get at here? So this is an actual thing I found using this approach. So this is a beautiful example because they have really similar slopes in pericenter and apocenter, and we have actually pretty good sigmoid fit. And on the right, you can see the actual orbit of the star in the XY plane over time, where blue is earlier times and pink is later times. And you see that the star does move in. Okay, so now that I have these stars that I flagged as having large radial changes, I can ask questions like, what is the radial distribution of these stars? What is the starting radius of these stars? Do they happen more frequently in certain radii than other radii? What does it look like? What do we look like in the plane? This is a very preliminary plot where in orange, I am just shading the bar length, which I estimated by a Fourier analysis. It has a thickness because the bar length changes in time, as we talked about a little bit in Binod's talk. And it could be a little bit thicker because there's also ambiguity in, how do you even define a bar length? I know Martin and Elena have different approaches. I know probably everyone in the room has their favorite way to define a bar length, which we will not get into yet. And then I also shade co-rotation. Co-rotation should actually be a thicker wedge, as you saw in Binod's talk. But this is just my very twiddles co-rotation, where I took the rotation curve versus radius, and I said, where is the rotation curve over r equal to the pattern speed at that given time step? So again, this has a thickness because it's over time. But again, it should also be even thicker because I'm just assuming a nice, perfectly circular orbit. But even from this super, super simple thing, you see that it seems like a lot of stars do have changes around where you would expect co-rotation to be. You also see sort of a dearth near where the bar is. And then you see another peak again in the very inner regions where things are just wild. It's the Wild West in there. Things are changing all the time. So then you can ask more questions like, where do stars in different annuli go? This is just one example of a plot. I have approximately 1 million of these plots at different time steps, different radial bins, apocenters, pericenters, yada, yada, yada. But I just chose this one to show because it's about where the co-rotation bar is here. So that's between 4 and 5, and this is an annuli from 4 to 4.5. And you see that the apocenter distance distribution is pretty tightly peaked at 1 gigayear, and then that spreads out over time. So just because you start out near this radius does not mean you're predominantly moving in the same direction. Things are moving in different ways. I also just picked pericenter to show because apocenter to show because apocenter is where you would expect a star to spend most of its time. So more questions to get at the original questions. So what trends do we see? If we define 4 kind of classes here of things with sigmoid fits, we can look at things that have pericenters and apocenters that both move in, things that have pericenters and apocenters that both move out, things that have pericenters that move in, apocenters that move out, and vice versa. So you would expect when you have a cohesive movement of pericenters and apocenters both moving in or both moving out, that might be co-rotation. That's kind of where you would expect co-rotation to affect your star. And then you might see the funkier stuff where, pericenter moves in, apocenter moves out is a different resonant interaction there. And do these kinds of changes occur more frequently at different radial bins? Where again, the radial bin is just defined as my 1 gigayear start time. Kind of arbitrary, but you need to start somewhere. And do these changes tend to happen at a specific time range? And again, time is also linked to pattern speed. What is actually the frequency that you're interacting with at a given time. So these are my most likely co-rotation resonance plots. So things with pericenters and apocenters moving in, pericenters and apocenters moving out. You see that you are much more likely to have pericenters and apocenters moving in the very inner regions and then around co-rotation and beyond. Pretty similar shape for peris and apos moving out, but less frequent in the inner regions. And these are my favorite. These are the oddballs. These are the other resonant interactions. Something I find really interesting here is that if you have your pericenter moving out and your apocenter moving in, you're almost certainly within the inner 2 kpc of the galaxy. So that tells us about what kind of interaction that could possibly be. But again, for the general shapes of these plots are not the same. So we can already see that there are different kinds of resonant interactions happening here in different places, happening with different strengths. You're moving different stars, different numbers of stars. I also want to point out that I did not scale the axes the same, or the y-axes. So these are larger in magnitude. There's more stars doing this than moving in and moving out, or out and in. So these are less frequent and different resonances as well. So as I mentioned, the sigmoid is not exactly perfect, and I can do a better job. I can do likelihood analysis. I can do a full actual regression. 1,000 stars and half kpc annuli bins is not exactly taking advantage of the absolutely massive simulation we have. So I got to scale up as well. And I also want to better characterize these interactions, figure out what's actually happening here instead of just, looking at plots and saying, this seems like it's probably happening around here. I also want to compare to different simulations. I think it would be good to look at things with just a bar, just spirals, even just different simulations that also have a bar and spirals, just to see how initial conditions affect this and all of that. And I just want to give I want to give a big thank you to everyone who helped organize the school, Catherine and Adrian, but also everyone who made coming here to the CCA possible, security, the kitchen staff, the office staff, the wonderful AV people making this presentation happen. I want to thank everyone. I also want to thank all of the mentors, all of the students. I want to especially thank Jason, Ellen, and Martin. And I want to give a huge, huge thanks to Rachel. She's my hero here. She made it so that we could actually use the simulation. At the beginning of the summer school, it took 3 hours to trace a single particle through a couple hundred time steps. And now it takes 30 seconds or less. So everyone say thanks, Rachel. Thanks, Rachel, and also thank you, Carrie.
So super interesting. I'm What I'm curious about is the stuff that you cut out, the sort of slow secular evolution. Did you cut out like is that cutting out most of the particles, and do you understand that part, or is it really are you really thinking of all of the radial migration as a sum of these resonant interactions?
So all of the plots I show from this one on are cutting out, that more gradual change. But even from this, you can see that for each half KPC annuli bin, which started at 1,000, it's fewer than half are having more dramatic changes. I think that the gradual changes are also really interesting, and that's why I want to do a more advanced method for finding things that are moving, because I think that that's also what we're going to be seeing as observers. Like we're going to be seeing a lot of this gradual change. And it's fun to look at the oddballs. It's fun to look at the ones that had, resonant interaction and changed a lot. But I think we need to understand the bulk motion as well. So I think that that's something I want to do moving forward, is not cut it out, but try to characterize it and understand it. But for now, I was trying to separate them out and sort of just tease out things that look weird.
Great. Thank you.
Okay. Okay, for these stars, I did like a bunch of different things. I tried a bunch of different things. So for these plots, I just took the average slope in that annuli bin, and then I just said if it's above one standard deviation of that. Obviously, how severe I make that cut really changes what comes out. If I say 3 standard deviations, I have like 1,000 stars total. So I wanted to have like enough stars to sort of look at, but it is arbitrary in a way. So I have to really do a more thorough analysis of what's going on here. But just to get a sense of what's happening, I had to just pick something and stick with it and look at what came out.
Hi, Carrie. Very nice talk. I had this question about the funkier stars where the pericenter and apocenter behave differently. So, do you have an idea of what kind of resonances are doing this? Is it the outer Lindblad or inner Lindblad resonances which are doing these things? Because this is definitely not co-rotation resonance.
Yes, certainly not co-rotation. That's like the main thing you can get from this plot is something else. I mean, for pericenters moving out, apocenters moving in, you would have to be inner Lindblad, right? You would have to be inside of co-rotation. But there's also some like 3 to n things that could be there. I would guess the same thing for pericenters moving in, apocenters moving out. I think Martin has a much better handle on this than I do, but that's just my general feeling is that for these plots, it's probably, or at least inside of co-rotation, probably inner Lindblad and 3 to something.
So what is the relative number, like compared to co-rotation resonances, or what percentage of stars do this compared to, like, have you checked like which one is more dominant? Is it the co-rotation resonance or is it the?
It really is the pericenters and apocenters moving kind of cohesively. So things that you would expect to happen more around co-rotation.
That makes sense.
So these in total are like 1,000 or so stars in my selection, like 1,000 to 3,000. And then for peris and apos moving in different ways, we're down to like a couple hundred.
Okay.
So it's much less common, but maybe more interesting because not looked at as much.
Okay, cool. Thanks.
So I guess my question is, one of your plots seemed to suggest, and I think it was like several slides earlier, maybe on slide 8, if I can remember correctly. Yeah, it seems to suggest that your stars are on average moving out more than moving in. And the question I have is, can you make a prediction about what you expect the metallicity distributions to look like, so you can make this an observational result? Or can you make this an observational result?
Yeah, I do want to say that it looks different for each annuli. So it's not necessarily always the case that you're going to be moving out. from like 4 out, it generally does predominantly move out. I don't have a great observational response yet, what I would expect from the metallicity distribution. Yeah, it's not cut in stone that it's going to be universally moving out. On average, moving out is more common, but it's only in like outer parts, and then in their parts, it's just kind of like getting pushed in. So I can also show sort of the bulk motion. Oop. So in this one, you do have this like nice wide tail moving out, but then you also have stuff that already had smaller apocenters moving in.